It has nothing to do with satellite design.
I know, but I'm just saying that I saw the satellite design homework.
Oh, yesterday?
Yes.
He posted automatic controls homework.
I haven't seen it yet.
You sure that wasn't automatic controls homework he posted?
Just making a statement for you.
No, I'm saying you sure that wasn't automatic controls
I'm
homework?
100% sure.
So you have assignment number 1 up on Blackboard, okay? This will be due Thursday.
Like next Thursday?
Yeah, the Thursday from a week from now. And what we'll do is exam 1. We'll either do it on Monday or Tuesday. Okay. So be prepared for Monday afternoon when the lab happens. Monday is your lab, right? Controls lab.
Okay. Are we going to do a lab?
Huh?
Okay. Are we going to do a lab that day?
Yes, we'll do lab as well.
So what about people who are going to leave before though?
That's the reason I'm thinking.
Okay.
How many? Just 2 of you all, right?
Just 3.
3 of you all. Okay. If not, we'll do it on Tuesday. But be prepared for Monday, okay? But you'll have sufficient time between now and
Can I look at the assignment on my laptop?
You uploaded a satellite design assignment too, right?
No, not yet.
No, that's what I'm
Upload
saying,
that.
bro. You uploaded automatic
I'm sorry,
controls.
Torres, okay?
You didn't listen to me.
People make mistakes.
You don't read your email.
Not everybody's perfect like you.
No, that it's clearly said in the email. It said automatic controls.
You got an email from this class?
Yes.
When?
Yesterday. I'm pretty sure you sent it to everybody that's on the classroom.
Well, we're going to see about that.
They don't check their email, Dr. Sunday.
Hmm?
They don't check their email.
I'm going to do one of the optional homeworks from that assignment, okay? Optional problems. And I'm going to try to do, or let's see if we can do this. All right, so let's look at this problem. Okay? I think this will be better. This is your,
Assignment? I'm not there yet.
so the questions will be typically like this. So you have frequency and time domain modeling.
Oh, wow. There's a lot on here.
What is it?
Next Thursday?
You said it's 13 questions, Dr. Sunday.
We have 7 days to do it, Torres.
There are only 10 of them, which are 3 of them are optional.
They're not all long like that problem we
No.
did today. Okay.
There are only 2 or 3 which are really long. Most of them are one-line answers
Okay.
or one.
Anthony, don't say
Keep that in mind.
because
Okay?
I'm
There
telling
are-
you on time, all the time. Okay. I can't say that for you.
So
Actually, you missed the
what
first
you-
assignment.
We looked at translational system. Okay, we need to look at least one rotational system because those are very critical in the aerospace domain, right? So let's say you have.
So this is not a problem of the homework, Dr. Sunday.
This is not the problem of the homework. I'm going to do this from the textbook.
And did you pick the problems? Are they from the textbook?
Yes.
All of them?
In the homework,
Yeah, are they all from the textbook or just most of them?
I might have modified. I don't remember. Just check. All right. So look at this as a rotational system. Okay. Now here is the torque is applied. So this is, let's say, D. This is, you can call it K. This is D2, D1, and let's call this J1 and J2. And what you have is you have theta 1 and you have essentially theta 2 of T. Right? And you have a torque applied here. Okay? Okay. So here D1 and D2 are torsional dampers. Okay. K is a torsional spring. J1 and J2 are inertial. Theta 1 and theta 2 are angular displacements. Okay. And T is, you can call it angular force or torque. Okay. So you need to be able to model this as well. Typically what I'll ask you is find, let's say, theta 2 over T of T. Okay. This as the transfer function. Alright. This will be the time domain modeling. And then I'll also ask you find state space representation if output is theta 2. All right. Now keep in mind your impedances are similar. So if I do the impedance type of modeling for frequency resisting, take this J1 keep in mind, why do you understand the concept of inertia and how is it different from mass?
Does that say find S as separation?
Find theta 2 over T2 over T. What is theta 2? It's the output, okay? This is input. We're always trying to find the transfer function in terms of output versus input. Or here it is actually theta 2S. Okay, this is S. So if you look at inertia, why do we consider inertia only for rotational systems? Why not translational system? Any idea? Do you understand the concept of inertia? What kind of mathematical quantity is a mass? Guys, stop writing for a minute. This is very critical, so try to understand this. Do you understand what kind of mathematical quantity is a mass?
It's a number. It's an integer.
It's a number, not an integer, but it's a scalar, right? You can say it's a number, right? What kind of quantity is a inertia?
Inertia is a scalar, and it's a vector.
It's a matrix. It's a 3 by 3 matrix. You understand? If you look at inertia, the inertia matrix is generally represented as a 3 by 3 matrix. What that means is, when you're rotating something, the distribution of mass is also important. So think about it like this. If you consider a homogeneous sphere, okay, of a particular mass, and let's say let's look at a homogeneous sphere of, you know what a homogeneous sphere is. The mass is equally distributed, okay. Now consider something which is heavy at the center or not heavy at the center, and there are heavy masses on either side. Okay. You have a homogeneous sphere. Both of these masses are the same. There's one system where the heavy masses are on a lever, and then you have a sphere. Which one is easier to rotate?
One in the center. Which one's easier to rotate? The one that has the mass in the center.
A homogeneous sphere?
Yeah.
So you
How
have,
are we rotating it? Like, if it's two masses on the side.
so you have this, okay? And you have this one.
The bottom one would be easier to rotate.
I thought they're both still. Is it one circle or is it two circles?
The mass of this system and this system is the same. Okay, this is the first system. This is the second system.
But it's still one sphere.
Too much, yeah.
It's
Together, this mass is equal to this mass.
Okay, yeah. So they're not both one sphere apiece.
No.
Oh.
So it looks like number 2 would be easier to rotate.
Yeah.
Number 2 would be easier to rotate, right? So this one, when the mass becomes concentrated in the middle, all right? When you consider mass, what you're essentially saying is, you're looking at a concentrated mass at the, what is that point called?
Core. Focus.
Center of,
Center of gravity?
yeah, center of gravity or center of mass. Okay. So when you apply Now think about translational. Translational, which would be easier?
Be the first one to translate.
To move it in a linear direction.
Be two.
Two.
Or be one. Or
It'll be the same.
okay. Yeah. Sorry. No, I'm seeing what you're saying.
What you're going to do is you are going to apply a force at the center of mass.
Yeah.
Okay, of this, you're going to apply a force at the center of mass here. Okay, and you're assuming it is. You can practically say that all that is concentrated at that one point. What happens if you apply a force in the off of the center of mass?
You get a rotation.
You get a rotation. And depending on how far you go, right, the force required would be, if you apply less and less, because torque would be what? This force into that distance, right? So to rotate, the angular displacement, if it's the same, all right, or angular velocity is the same, as you go farther and farther, the rotational force required to achieve that angular displacement or angular velocity becomes less and less. You see, what did Archimedes say? Give me a lever and a place to stand, and I'll move the earth. Right? What that means is, even an object as heavy as earth, if you have a long enough lever, the amount of force required to move it, as a lever becomes infinite, the amount of force required will become zero. Okay, so when the distance tends to infinity, the force tends to become zero, and the product of that is the same. If there is a force required to move something, all right, and that force, if you are going to apply some kind of moment or torque, depending on how far you go, okay, that is the reason this inertia essentially identifies the distribution of mass of any system, not just the mass as one number, which is assumed concentrated at the mass center of mass or center of gravity. Okay, you understand? You understand the concept of inertia a little bit?
So if you had to explain inertia in one sentence, you had to explain inertia in one sentence, what sentence would you use?
Inertia is a distribution of mass. Distribution of mass. So what you do is you have a principal axis, so-called. Okay, so you identify a principal. For example, if you want to identify your inertia, you'll define three axes. All right, x, y, and z, because we know space as it exists in 3 dimensions. Right. What is the distribution of mass about the x-axis, y-axis, and z-axis? That is the inertia.
So you're saying J1 and J2 hold all the mass in the system? Is that what they're saying?
Yes, they are essentially mass, but they have to be considered as inertia if we are talking about rotational system. This is a rotational system. Okay, so J1 and J2 here will be what? 3 by 3 matrices.
Matrices,
Matrices, yeah. They are called tensors. Okay, you can see that's a tensor. Right. Now, the modeling does not change. Okay, so you can see that you have J1 S square plus D1S plus K into this would be what? Into theta 1 F, okay, plus or minus K into theta 2 of s equal to T of s. You got it? This is the same impedance approach we talked about. Alright. Now, similarly, inertia J2, what you're going to get is consistency. We'll do this. J2s plus D2s square plus K theta 2s equal to 0. Right? And if I take the inverse Laplace of this, I'm going to get J1 theta 1 double dot of T plus B1 theta 1 dot of T plus K into theta of T
Dr. Sunny,
minus, yes,
if you want to find your theta 2 s over ts, why are you converting it to time for? If it's already in frequency, why are you converting it to time? When you
is it in frequency?
We said the S was in frequency, right?
We have to model this.
Mm-hmm.
You'll be only given this.
Mm-hmm.
You have to arrive at this using the impedance approach. We did the impedance approach a couple of, I think last class and the class before that. So I've just used that. And we need that for this.
So you're not doing the one above it.
Huh?
So you're not doing the one above it.
We'll do this. These two are what we are doing. So we looked at, you'll get it. Here it is J2 theta 2 dot of T plus D2 theta 2 dot T K theta
So that's what I'll do after this.
minus K 1 T equal to 0.
Just a little bit of business on for you.
So for 1, you want 1, right?
Dr. Sunny?
Hmm.
Wait,
We'll see about that.
never mind.
You gonna do it?
So you have theta 2 of S equal to what? So you have these two and you have these two. You replace these two, if you want theta, replace these two by T of S and that, 0. Okay, so you have T of S here, 0 here. And what you're going to get is minus K into,
So the left side is the frequency domain. Left side is frequency domain, and you want to arrive there. The right side,
is the time domain.
okay.
I'll tell you why we need that part as well. Okay. So this is for arriving at this, right? Keep in mind, remember this. Ax plus by equal to x. Sorry. M. Okay. Cx plus dy equal to n. Now if you want to solve for x, you do dx by d. Okay. Dx is what? M n b d. Take the determinant of this. You take these two, replace this by mn. Okay, so here you're going to get, this is dx and d is simply a B, C, D. Intermediate. So I'm solving for theta 2. So I'm going to replace the coefficients here, okay, by Ts and 0. So you're going to get minus K into Ts, right? This is 0.
What? What are you doing?
He's trying to solve for 32S.
Okay.
He's just trying to skip some steps.
So here,
Alright, I got you.
my dx is what?
That was a rule.
J1 Kramer's rule, yes. D1S plus K, right? I keep this as it is. I replace, sorry, I
It's
need
D1.
theta 2.
Yeah.
Okay.
Wait, it's D2, right?
It's, yeah, you can call it d theta 2, okay? Alright. So if I need d theta 2, I'm going to take minus k. I'm going to replace these coefficients. Here it is minus k, here it is this thing, right? So I'm going to replace this by T of S 0. Okay, and d is what? J1 S square plus D1S plus K. Okay. Here it is minus K. It's minus K. K2S square plus D2S plus K. Okay, my theta 2 is what?
So, wait, you looking for D theta 2? D theta 2 or D theta
Theta
1?
2. Theta 2 is d theta 2
Over the D.
divided by d. Right?
Okay, so I thought if you're doing, but you use the values from D theta 1. I thought you just use the values from D theta 2.
What you do is if you want theta 2, okay?
Wait, I asked this quick question. I think. Okay, so before, when we did the matrix,
Hmm.
you took the first matrix, just everything on the left side. But this time, now you're including the TS in with your D.
This you start with this, okay?
So you start with D.
Right, this D is A, B, C, D, coefficients, okay? A, B, C, D. Now
Okay.
here remember X is theta 1,
Mm-hmm.
Y is theta 2.
So that's what I'm saying. So I thought, why don't you use the Y if you're looking for theta 2?
I have to replace the Y. If I'm looking for X, I replace X.
Okay.
If I'm looking for Y, I replace Y by coefficient. You
So-
start with A, B, C, D, okay? If I'm looking for X, I replace X coefficients with constants on the right hand side.
No, I see what you replace on the right hand side with the TS and 0. I thought the K is supposed to be negative K, and then J2 S squared plus D squared S plus K on the second.
This one?
Yeah, so I thought the negative.
This
K
you're clear with this?
Well, no, well, I'm kind of confused on the left side because you're looking for D theta 2, so I thought you put theta 2 values in there.
No,
So
theta 2. What is the coefficient of theta 2?
Y
Minus K.
minus K.
What is the coefficient of theta 2 here? This one, right? You replace those coefficients by these. If you're looking for theta 2, d theta 2 is this, theta 2 is this.
Okay.
You replace those coefficients by these. If you're looking for theta 1, so if you're looking for theta 1, this will become d theta 1. So that time you replace these two with these. You keep these two as they are.
For D theta 2, why is the first row, first term not 0 when it's theta 1 there? That's what's confusing me. Like, why is it J1 S squared plus D1S plus K? Because that's a theta 1. Why is that not 0?
That is how you solve for it. That's the Kramer's rule. So here you look at this.
Mm-hmm.
If you solve for x, you just keep as it is. Okay, that's the Kramer's. That's how you apply it.
Then why'd you put TS there and ignore the negative K theta TS?
You replace the coefficients. Again, go back here. So what are the coefficients? If you are solving for x, what are the coefficients? A and C, right?
Mm-hmm.
You replace A and C, whatever is on the right hand side.
Okay.
If it's dy, you take B and D and replace it with M and M. That's what I'm done with. Okay. So here, you're going to get this as, so d theta 2 is what? This minus this. So it will be K and Ts divided by this minus this. Okay. So you're going to get G1 S square plus D1S plus K, this multiplied by J2S square plus D2S plus K minus K square. Okay. And if you just, sorry, this is S, okay? You can call this as S as well. That doesn't matter, it's just a notation. And so if I take this off and put it here, this is my transfer function.
Ooh.
Wow.
Okay.
When we finish writing this out, could you go back over the matrix?
No, you have to do this. Don't see you. I cannot. I'm telling you.
Like how you went from the matrix to that equation. That's all I'm asking.
Yeah. So this. What is the determinant of this?
What are we looking at?
What is the determinant of this matrix?
It's just gonna be positive TSK.
Yeah.
Ks, right? It is this minus this.
KTS.
Oh, okay.
KTS. Okay, I just moved that here.
Okay.
Don't write. When you're listen. Don't write.
Oh, that's the
You,
answer.
if you listen, you'll understand. If you try to write it, you'll miss it. The numerator is determinant of this. Okay. So it is T of S, right? It is K into T of S. Is that clear?
Yes.
Mhm.
What is the determinant of this? It is this into this, right? It is this minus this into this. K into K is
K squared.
K squared and minus K squared.
Why wouldn't it be positive?
Because it's
It's
You
determinant.
square the K's and then you subtract.
That's how determinant is
sorry.
calculated.
Sorry.
We cannot redefine mathematics.
No, I just made a
we
mistake.
can Dr. Something.
We cannot redefine mathematics. Okay. So that's how, see,
Anything's possible, Dr.
you have to understand, don't take this any negative, but don't ask me, we cannot discuss the basis of mathematics, right? So what we do is we accept some of things. So you cannot ask me things like, why this is not positive? That's how so what is the determinant of this?
I think he just messed up for a second. I think he knew it. He just,
No, I'm saying, I understand, I totally understand. But ask questions, how do you take the determinant of this,
AD minus CB.
BC.
right? You're with me, Anthony?
Did you say BC?
This is AD minus BC.
How do you take the determinant of this?
That's
AD
You're going to
minus
be
BC.
specific.
Right, that's what I did, AD, okay, minus
Okay.
BC. This, what is BC here?
B K squared.
K square, right? Minus K square. Got it? Similarly, this is how it is done. Julian? This is how the Kramer's rule is developed. Okay, these two are coupled. So you have to just take it. If you want to go back and review, that is outside the scope of this class. You understand? We just adopt the Kramer's rule. Got it? All right. So here, this is what you need to give me, okay, in the exam. So this is, I just move this here. And this is what I asked you, this is what I got. Now let's look at this. Now here is your answer to another question, why I did this, right? This was the other question. So the state space modeling. We need this as the basis for our state space modeling. You get it? So here Z1 is what? Theta 1 of t. Okay. Z2 is what?
Theta dot T.
Theta 1 dot of t. Right? Z3 is theta 2 of t. And Z4 is
Theta dot.
theta 2 dot. Okay. Don't say theta dot 2. So the variable is what? And the reason I say that is, here what is the variable?
Two.
Theta 1.
Theta one.
Okay. Here it's the derivative of the variable. You understand? So that is what you say, theta 1 dot. So if you have Julian Jr., you say Julian Thompson Jr., right? Would you say Julian Jr. Thompson?
No.
That's all. So Julian Jr. is the basis. You understand?
Yes.
So Julian Thompson is the basis. Julian Jr. is not the basis. This is like the junior.
Like what you should have named your first kid.
You understand? The dot is like the junior.
Okay.
So dot will not exist if there was no Thompson. You understand?
Yes,
So
sir.
this is like Thompson. This is Julian Thompson Jr. You won't call it Julian Junior Thompson. You got it? So this was the Julian Thompson was the basis. You understand? So this becomes the. So now you have these are the so theta 1 dot, theta 2 dot. They are system variables, and Z1, Z2, Z3, Z4 are the state variables.
Question.
Yes.
Can we, since we technically did already find theta 2s, can we convert theta to s2 time, and then that be our theta 2?
So here the representation is different. Okay, you'll see that. So here you have theta 1 dot is, sorry, Z1 dot is what?
Z1 dot is theta 2.
It's Z2, right?
Uh-huh.
Or let's say theta 1 dot, right? Which is equal to Z2, alright? Similarly, Z2 dot is theta 1 double dot.
Or C3.
This is not
Or
Z3.
Z4. No. Hold on.
Yeah, so what you do is,
Hold on.
for this one, you solve for
Too far.
here, from here.
That's what it is.
Okay, so you're going to get minus, I'm going to write it, minus K1, K divided by J1 theta 1 of t minus D1 divided by J1 theta 1 dot of t minus K of J1 theta 2 of t plus P of t. Okay, I have just solved for, from this I just solved for theta 1 double dot. You see why this is important?
Yeah.
Okay, I just solved for that. I put everything on the right hand side. Okay, so this is what, now I'll just write it in terms of minus K over J1 Z1 minus D1 over J1 Z2 plus K over J1
Z3.
Z3 plus P of T. So similarly, you have Z3 dot is Z4. It will just be theta 2 dot. Okay, Z3 dot is theta 2 dot, which is Z4. And Z4 dot is again theta 2 double dot. And I'm going to write this directly. K over J2 G1 minus K over J2 G3 minus G2 over
What did you just erase, Dyson? What did you just erase?
So there is no dot over B2. That's a constant, right? So
Yeah.
these are constant.
I'll make sure I didn't put that on my paper. Let's check that paper. Top. Still up.
Okay.
It's from the cocaine, isn't it?
So if you have now your Z dot, the big Z dot, right,
There's still cocaine in your nose.
equal to what? We're going to essentially write Z2, right? 0, 1, 0, 0. Here it will be
0.
minus K over J1 minus D over J1 K over J1 0. Here it will be 0, 0, 0, 1. Here it will be
Over J2.
K over J2
K over J2.
0. Because
Oh, yeah.
there is no Z2.
Yeah, I see it. See now.
K over J2, the negative, minus D2 over J2.
Yeah, like another matrices.
And this will be, so here I'm just going to write this as Z. I'm going to tell you what this Z is. We have already discussed this. Plus, you have
0.
0. So here, there is actually a mistake. 1 over J1.
Oh, yeah.
1 over J1, 0, 0. And this is T of T. Okay. Now, I told you this is very critical. If output is theta 2, so your Y would be 0, 0, 1, 0, Z. Okay. Now keep in mind, what is Z? I'm just going to write it here. Z is Z1, Z2, Z3, Z4. So accordingly, Z dot would be
Dot 0.
Z1 dot, Z2 dot, Z3 dot, Z4. Okay. So this corresponds to this, and this corresponds to
What's the rows stand? What's the rows stand for?
these.
Yeah, you label the column. Well, what's you label the columns? I'm trying to say. Okay, so you saying?
So if you look at, so let's look at Z1. Okay.
All right,
Z1 dot, right?
all right.
Z1 dot is what?
Theta.
Z2,
Right.
right? So you have 0 into Z1, 1 into Z2.
Okay.
Everything else is 0, right?
Okay. Yeah. That's what you're saying. Never mind. I got it.
Okay.
I just forgot it.
So here, this is the critical thing. I think you will probably be able to do this. Here, you have to look at what is the given output. Output given is theta 2, right? what does it correspond to in terms of, this is a system variable output. What is it? What is the state variable of that? What is the state variable of theta 2?
Dot theta 2. Z3 and Z4.
So keep in mind, these are the state variables. These are state variables. Thetas are theta, theta 1, theta dot are our system variables. Okay. So if this is a system variable, the state variable is Z3, right? So if you look at what is this Z, it is Z1, Z2, Z3, Z4, right? So you have 0 into Z1, 0 into Z2, 1 into Z3, because output is theta 2.
Why in the beginning did we make our Z1, 2, 3, and 4 those specific values?
Right, so that's a good question. Now, typically what I would, rule of thumb is, what is the order of the system?
Second order.
This is a fourth order system. In that,
Yeah, we talked about that.
we talked about this, right? Because there are two, each of the equation is second order, but these are coupled, they cannot be separated. So together it's a fourth order system, right?
Yeah.
If there are, it's number of state variables, you can take it is equal to number of the order of the system. You got it? If it's a fourth order system, you take 4 state variables and equate them like that.
Can you make of these specific state variables?
These state variables are, you can call it H1, Hunter 1, Hunter 2, Hunter 3.
But you would make them these specific values.
Yes, so these are
every time.
system variables. These cannot be changed. So these means, see, look at what these, the Z1, Z2, Z3, Z4 are kind of abstract. They don't have a physical meaning. Okay, but what does theta 1 have a physical meaning?
Yeah.
What is theta 1? What would you call it?
So, angular momentum. No.
Angular displacement. Right? Angular displacement of what? Of J1, right? By how much it is displaced. So similarly, theta 1 dot is what?
It's the velocity of.
Angular velocity. Got it? But Z1, Z2, they are simply state variables. They are only meant for, they are representing certain system variables. But they don't necessarily have, because what do you know velocity is? Velocity, you typically know it as a first derivative, right? Derivative of displacement. But you see, velocity here is not a. You understand? So here, the state variables are more abstract. The system variables, you can make sense of them. You can connect them physically. Got it? And then these. So what this will allow you to do is, you understand. Try to get a feel of how much mathematics is in here, or what are the different kinds of mathematics in here. We had a physical system. We did a block diagram. This is the physics of the block diagram expressed as frequency domain mathematics. We applied inverse Laplace to get the differential equation format of mathematics. Okay, this is the matrix form of that same mathematics, of that same system. This is a matrix mathematics. This is a differential equation mathematics. This is the transfer function form of mathematics. All these give you different tools. Different mathematics give you different tools to solve for. What you're interested in is in the context of control is, if I want to control theta 2, these are the dynamics, okay? So what will you vary if you want to control theta 2?
Torsional. Torsional force.
Torque, right? Torsional force. That is the only thing. The input is what you can vary, and the output will accordingly respond. You got it?
How did you get? I forgot. How did you get Y? How did you get 0, 0, 1, 0?
So I told you this is the output, right? So Y represents the
Output.
linear combination of output.
Okay.
Here the output only is theta 2. if I had theta 1 and theta 2, got it? Then it would be this 1 0 1 0 that. Okay.
Because that's just that Y statement is the SMS representation if output is theta 2.
Right.
What does that? What does that mean?
Why is it not
Right.
0 1 0 0?
If it is now why we are doing this? We can even do theta 1, right?
Cool.
Here. We could, right? It depends on what you're interested in. You understand? What you're solving for. In an aircraft, what are the different outputs? You can essentially, what are the three outputs?
You can do speed, you can do altitude,
Pitch, roll, and yaw.
Pitch, roll, and yaw. So this theta corresponds to pitch, roll, and yaw. You understand? So it will be theta 1, theta 2, theta 3. And how do you achieve that? Torque. You understand? Especially if you're looking at unmanned systems, where will you apply the torque?
Where?
If you're going to
center of
pitch
gravity? About the center of gravity, there's at the wings.
at the ailerons,
Oh yeah.
right? You'll torque the ailerons. You understand?
For pitch? For pitch, you said?
Mm,
Oh, that's the elevator. What are you talking about? For pitch, or are you talking
For
about
pitch,
roll?
you'll do this thing, right? Ailerons, right?
For pitch? No, you use the elevator.
Huh?
Elevator.
Right.
Yeah.
For the
For the turn, you use aileron. So aileron is roll. The vertical axis is yaw,
Right.
and that's what your rudders
right.
normally per se. Yeah.
So essentially, you're torquing.
You been in a plane before or something?
No, I haven't.
That's wild.
Have you been in one?
I have. That's crazy.
Maybe you can teach me something you learned in the plane.
All right, man. Do a lot of GTA flying too.
Oh, really?
I know all the safety procedures.
Okay. So you're
I know my ground school.
You see, the pitch, roll, and yaw is very common, right, for all aircrafts. But you see, this changes for an aircraft.
Right.
Depending on, these are the values which change, the dynamics. And then, to achieve this, you're going to apply a certain torque, and that torque is going to be multiplied by the dynamics. Okay. So if I were to move one of y'all, or let's say all of y'all, this will be the linear displacement, right? But how much torque I need to apply will depend on your dynamics, on how much you can resist or how much you can. So your system is different compared, and that is what you're doing. You're trying to develop the dynamics of the system.
So, Dr. Sunny, this is a pretty long question, per se. I noticed a lot of problems we do in class are pretty long. Are they going to be like that on the test? Or going to be like
Yes, so what you need to do is, it's not long. So I'm going to limit to 2 masses, not more than 2 masses.
Okay.
See, if you look at the exam, okay, these two there will be one problem like this. Most of the others will be simple. Is that okay?
Are you still doing multiple choice, true or false statements?
We'll try to do that.
I don't know if you did the same as you did.
Yeah. But this is very, very critical. As I told you before, from here onwards, a electrical engineer or an electronics engineer might be able to do the same job as you, because controls is taught across engineering disciplines. Okay, so even a chemical engineer is taught controls. All right. Now, what we do here, this analytical dynamics, is what should be your bread and butter. It should be what you should be able to do. Okay. Any questions?
No,
sir.
But I need to study.
Yeah, just get started with the thing. Please bring